So we've now replaced the variac and the isolation transformer with this 12 volt to 230 volt inverter. And what I've got to do now is I've got to populate all of these voltage and current readings using this plugging energy meter fed by the inverter. And then we can do some comparisons between, well, I guess we're comparing a few things, aren't we? We're comparing the difference between true RMS meters and meters that aren't true RMS. And we're also going to be comparing the difference between measurements taken using a proper sine wave and you know, output voltages from this inverter, which are anything but sinusoidal. As I said earlier, they call it a modified sine wave, but as we're going to say, it looks nothing like a sine wave, it looks more like a square wave. So we've got lots of different things going on here, which all just really go to confuse everything. Well, they confuse me anyway. That don't take much though. Right, okay, so let's switch on. So switch on, and the Fluke 175 true RMS meter says the voltage is 132 volts. So I'm going to write that in, 132. And let me see if I can, I'm going to have to stick my head in front of the camera now to read the AVO meter. Okay, I'm going to call that 39 milliamps. Right, so let's try using the Tech 4 next to do the current measurement. The Ryobi Tech 4 meter is indicating 16.7 milliamps. So I'm just going to write 16 milliamps for that. Let's move on to the BK precision meter. The BK precision meter indicates 4.8. What have we got next? We've got the Exotech, which we can't do, and we'll do the scope in a minute. I've got the Fluke to do, haven't we? Let's do the Fluke meter current measurement. So I'm going to replace the Fluke with the BK precisions. Just double checking myself now. So basically the I'm guessing the Fluke meter, the 175, is just giving me a totally garbage reading. It's saying that it's 197 milliamps. So we'll write that down, 197 milliamps. Might as well just get a voltage reading here. 232. $224. And the final voltage reading we just need to do using the AVO 8. And the AVO meter is indicating 224 volts. Well, I don't know about you, but I'm starting to lose the will to live. But we've got our inverter plugged back in. Let's switch it on and have a look at the voltage waveform on the scope. So here's the horrible output from the inverter. What have we got here? Channel 1, cycle RMS. So this is showing 118 volts. We've got to double that because we're measuring it across a potential divider. So if we times that by 2, we get 236, don't we? So let's write that down in my little table here, 236. Now I think probably what everybody wants to see is the current waveform again. Let's have a look at that. And hopefully you can see that it's back to showing us these horrible little spikes. Let me bring you in. So that's the current waveform. Whenever the wave you know, transitions from one cycle to the next, we get these really horrible current spikes. So for most of the time, the you know, there's no current going through the capacitor. It's not conducting. God, that's a different argument, whether or not current goes through a capacitor. You know what I mean. But most of the time, you know, there's no current flowing in the circuit. It's just restricted to these huge current pulses. Let's just zoom in on one of those current pulses and see if we can just determine roughly the magnitude of it. I don't know, for some reason it doesn't want to measure the currents. So what we're going to do is, or the only thing I can do is to try to come up with an RMS value longhand, which is basically a complete pain in the arse, but we'll I'm going to have a go of it. And again, I'm likely to get it wrong because again, haven't done it for 30 years and I probably wasn't sure how to do it then. Well, I'm sure most of you have noticed that even at the best of times I actually try to avoid doing maths, and yeah, there's a reason for that. I'm just pretty rubbish at it. But we're going to have a go today. I don't know if we'll get the right answers or the wrong answers, but it'll be interesting to see your comments at the end of the video. And if you think I've got it wrong, then leave a comment, and it'll be interesting to see what you think about this. Anyway, let's crack on. So root mean square. Well, when you're actually trying to do the root mean square process longhand, it's actually to look at the letters backwards. So what you actually need to do is you need to do the square, you need to take the mean. Now mean is just another word for average, and then you need to do the square root. So in effect, what we're actually going to do is we're going to look at our waveform, and we're going to split it up into lots of little samples. So that's what these A's are here. So basically A1 is your first sample, then A2 is your second sample, A3 is your second sample, and then for however many samples you have, you just keep adding them. Now if you just note here that the A is squared, so your first sample you square it, your second sample you square it, your third sample we're going to square it, and well, ad infinitum. Now the letter N here just refers to the number of samples you've got. So if you take an average longhand, you maybe take 4 numbers. So you've got 4 numbers. What you do is you add the 4 numbers together, and then you would divide it by 4 because that's your number of samples. So that's the squaring process there. So we take lots of samples, we split our waveform up into more samples the better really. We square each of those samples, then we divide it by the number of samples we've taken, and then we take the square root of that, and hopefully that should give us the RMS. Or that's what I think anyway. I guess we'll have to suck it and see, won't we? Now these pulses look fairly symmetrical, positive and negative. So what we'll do is let's just try and characterise one of these current spikes. And I'm going to press run stop before this thing melts itself, because it does get hot when it's running from the inverter, so I can turn that off now. So right at the corner of we've got one of the waveform transitions here where it goes from positive to the negative half. It's going positive on this side here, and we can see that we get this this pulse of current. So as I said, I think that the positive current pulses and the negative current pulses, I'm pretty sure they're all symmetrical with each other. So what we can do is we can look at one of these pulses, and we will use the same one. We'll measure the characteristics of this, and we'll use it for all the other current pulses. So first of all, how many time divisions have we got? Let's just see. We're going to say that this current pulse event lasts 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to say it lasts 10. So I'm going to write these down. I'm going to draw up a little table. 2, 3, 4, 5, 6. And I think I'll write the timing in this column for what it's worth. So 25 microseconds per division. Now in this column, let's write down the voltage. So I'm going to use this as our first voltage here. So what I'm trying to do basically, I'm trying to separate this waveform into lots of little discrete measurements, and then we're going to do some horrible, well I suppose it's not horrible maths. We're going to have to try and add all these together, which is just going to be a total ball ache, but that's what we're going to do. Right, so the first one, using the cursor, it says it's 16.6 volts. What I'm trying to do is guess what the average current is for the time it's in that like time zone there, but kind of your guess is as good as mine. Let's go for 11.8 volts. I'm going to go for 8 volts for that one. Now those 10 sample points for the current pulse, I've plotted them down on a chart here. So again, starting at time 0, our first sample was 22 volts. Then we've got 15.8, 11, 8.46, 4, 3, 2, 1 and 0.6. Now in the next column here I've actually plotted the current because this voltage was actually going across our load resistor, which was 10 ohms. So the maths is quite easy, we just basically have to shift the decimal place. But it's interesting to note there that at our first sample, effectively at time 0, our maximum point in our current pulse was actually 2.26 amps. Then our next sample, again they drop down from there, so 2, 1, 1, 0.84, 0.6, 0.4, 0.3, 0.2, 0.1, 0.006. Now I've plotted that out on the graph. I didn't have to plot it out again. All I've actually done is change the y-axis here. I've just kind of rescaled it and I've changed it from voltage to amps. So I've just shifted a decimal place. But I've shown the calculation there just to make it, if it wasn't completely clear. So I took basically 22.6 divided by 10 equals 2.26. And we did that for every measurement and I've plotted it on the graph. So when we're talking about the average RMS, what we've got to do is we've got to add up the average for the current for all the sample points in the waveform. Now we've already said that there's actually 4 current pulses, so we're going to have 4 lots of this, if you like, 4 of these. But for the rest of the time, let me get the other graph out. So there's our 1, 2, 3, 4. But for the rest of the time, the waveform is actually doing nothing. You know, there's no current there, there's no current in that bit, there's no current in that bit, there's no current in that bit. Now, our sample points that we took, oh, I'm going backwards and forwards, aren't I? Do apologise. Our sample points were every 25 microseconds, and our total cycle time was 0.2 milliseconds. So how many samples would you have in the whole waveform? Well, basically we have to divide the 0.2 by 25 microseconds, and what you'll find is that's how you get a number of 800. So we've got 800 samples in our bag in total. Now just going back to the table again, remember that what we need to do is we need to add together all the amps squared. So again, I've just plotted that out again. So we've got 2.26 multiplied by 2.26 equals 5.1. 1.58 multiplied by 1.58 is 2.49. So we square each of these. Now once we've got all of these squared, we actually can just stick all the numbers into our formula. So let's have a go at that. So going back to our formula here, we've got our first sample squared plus our second sample squared plus our third sample squared. And you probably can't see on the camera, but I've written all the samples down there, squared them all together. So that was for our first current pulse there, that train of numbers. And then we've got our second current pulse that we're going to add to it. And then that's a third current pulse we're going to add to it. And then there's a final fourth current pulse that we're going to add to it. Looking at the current waveform, it wasn't at a high value most of the time. In fact, most of the time the current value was actually at 0. But the number of samples we worked out earlier, it was actually 800, so that's where we get the n from. So n is the cycle time, which is 2 milliseconds, and divide that by the sample time on our scope, which was 25 microseconds per sample, and that gives us a number, and it gives us 800. So if you add all those numbers together, you get this. You get 41.52. Divide that by our 800 samples, and if you do that to that and then square root it, take the square root of the answer of that, you get 0.227 amps. Well, you know, I think it's about time we wrapped up this little series of videos on the inverter and the RMS measurements. And you know, the whole experience has reminded me of something that the wife said this morning. Apparently the whole thing was deeply unsatisfying and it really wasn't worth the effort. So what I've got here is a list of all the numbers and measurements that we'd taken. I've got all the measurements we took for the various pieces of equipment, and the top one here, sinusoidal wave, that was just for the straight mains input we measured going into this plug-in unit. We've got the sinusoidal input wave, which is being derived from the isolation transformer, then the variac. Now the second set of readings that are taken, again we were using the same plug-in monitor as our load, but all these sets of readings here are with a various piece of test equipment fed from the inverter. So these measurements are for a sine wave input, and these are for the modified sine wave, which is a lot like a square wave. So here's the horrible output from the inverter. So we'll do the sine wave inputs first. So this table here is the measurements that we took using various pieces of test gear, including the AVO 8, the Tech 4, the Fluke 175, the BK Precision 5491A, the Exitech. I keep getting that wrong. It's Exitech, isn't it? I think I might have written that down wrong. But that's a source device. It provides AC mains at various frequencies and voltage. And we tried the monitoring plug plugged into that. And then we've got the measurements that we took using an oscilloscope, which was the old Tektronix TDS 2022B. So very quickly, just going through the voltage readings: 230, 229, 230, 230, 230, 232. So it really doesn't matter for a sine wave whether or not you use a true RMS meter or a non-true RMS meter. There's actually pretty much no difference between the readings, and we wouldn't expect there to be any difference because the AVO 8 and the Tech 4, they kind of they assume that it's a sine wave, and they apply a correction factor for working with a sine wave. So the voltage measurements were all effectively the same, and all the current measurements were effectively the same as well. The AVO was slightly low, but if anything that was probably just well, it could have been calibration, or it could also just be my reading error, having to read something off you know, a needle and pointer analog display rather than a digital display. But all the same, 48, 48, 48, 48 milliamps, voltages and currents all coincide with each other, no problem whatsoever. So all that's good. So regarding using pretty much any type of meter for measuring straight AC out the plug socket, happy days, no problems. However, if we use the same instrumentation again, but this time we feed the plug-in wall wart monitor, if we feed it from the modified sine wave inverter, we get some quite different results. So we look at the AVO 8 meter and the Tech 4. Now remember that these are both non-RMS, they're not true RMS measurements. They're making it up, they're assuming that the waveform is going to be a sine wave, and then they're applying an internal correction factor, if you like. I mean, the AVO 8 just does it, you know, analog style as a function of the resistors and capacitors inside it, whereas the Tech 4 is kind of more applying a digital correction factor. But they're both making the assumption it's a sine wave. So when you look at that horrible square wave that's coming out of the Tech 4 inverter, both of these meters read low. So if you were measuring the output from one of these modified sine wave inverters, you'd probably be wondering, why am I not getting the equivalent, why am I not getting 230 volts out? My meter's only indicating 224. Well, you are getting the correct 230 volts out. The problem is your meter that you're using isn't a true RMS meter. Is it worth buying a true RMS meter for the sake of the difference? Well, I guess it depends on what you're doing. If you're working with inverters a lot, and especially really cheap and nasty modified sine waves inverters, maybe it is worth paying the extra and getting an RMS meter. But for most of us, and probably me included, we don't really get a huge advantage. You look at the true RMS measurements. Well, we've got the Fluke meter that indicated 232 volts. The BK Precision showed exactly the same, was 232 volts. we couldn't do the same measurement on the Exitec source meter because we couldn't connect it to it because it won't output a square wave. The TDS 2022, well, the readings I got were a little bit high, on the high side. They were also a little bit high when we were doing the measurement just for the sine wave input as well. So I'm really suspecting that that's just, you know, like a kind of calibration issue, the basic accuracy of the scope, and also probably the fact that lots of things are adding to that lack of accuracy, like we were using time 10s probes, and we were also taking the measurement across a central divider. So I'm guessing all those things added up to make a few volts difference. But, you know, you really wouldn't complain the difference between 236 and 232. Yeah, it's not the end of the world. Now, more interestingly maybe, these are the RMS values that we calculated. And you saw me doing the longhand calculation for the current waveform. Well, I also did the same calculation looking at the voltage waveform. And again, looking at the voltage, when I calculated that longhand, it was 242 volts. And that seems quite a little bit higher than the other readings we've got, but it's also not a million miles out. So it's possible that I've made a mistake in the calculation there. Maybe I've not divided by quite enough data points, or I've made an error. But I'm kind of guessing there that that's probably 242. I mean, it's not like I've come out with a reading of 1,000 or 6 or 4. I mean, 242, I'm in the ballpark, aren't I? So did I get my calculation correct? I'm not certain, but I'm not a million miles out, am I? And I was using that as a little bit of a confidence factor. The reason I went away and rechecked it again is because obviously I had no idea what answer I was going to get for the current measurement, which is this value here, 227 milliamps. And what I think is interesting, that none of the meters, apart from the Fluke 175, gave anything like 200 milliamps. And in fact, when I plugged in the Fluke meter, I actually ridiculed it. I said, 192 milliamps, it's never going to be that. I'm guessing the Fluke meter, the 175, is just giving me a totally garbage reading. It's saying that it's 197 milliamps. Well, when I did the calculation longhand, I'm not so sure. So the problem here is that the waveform are really horrible current spikes. They're very sharp little pulses, and I don't think that any of the equipment I was using here was probably really optimized for measuring those type of current pulses, and I think the meters just couldn't cope. I also tried to look at the RMS cycle measurement using the oscilloscope, and I wasn't able to do that either, because I just couldn't get the RMS measure function to settle on the oscilloscope. I tried increasing the sample time, I tried different trigger methods, I tried making the waveform bigger, smaller, shifting from left to right. But what I think the problem was, I don't think the scope could really, it didn't know what the start and the end of the waveform was, because they were kind of just arbitrary pulse spikes. And I think that's why we had trouble with that. That's why the needle was, why the display was just flickering around. I don't know, for some reason it doesn't want to measure the currents. But I'm semi-hopeful that, you know, that 227 is in the ballpark with the 192 for the Fluke measurement. So perhaps, you know, perhaps my calculation was right after all. So I think in conclusion, all I've really got to say is measuring RMS voltage and current for any waveform that deviates much from a sine wave or has particularly sharp edges, fast rise times, square waves, it's going to be problematic. It's at least going to be problematic to me, and it has been. I'm not sure if any of these answers are right, and I'd love to hear your comments if you think any of these are correct or not. So that was a little bit unsatisfying really. I haven't got an answer. I think my final conclusion would be is don't buy one of these modified sine wave inverters. The output from them is horrible. You certainly risk damaging your equipment, because when we plugged this into it, it got red hot because we were getting these huge current spikes. You're not getting your device drawing current over the full main cycle. You're only really drawing current at these, whenever we get these transitions, and we get these big spikes. And I think that probably explains why some of the equipment we plugged into this modified sine wave inverter, it makes a horrible noise. And I don't know, I think it might have been around the 400 Hertz mark, which I'm kind of guessing was to do with just the way these spikes are being prevented. You know, you're getting these pulses of current, and you know, if you've got anything that's got a transformer in it, or maybe a motor, it kind of rings it like a bell. Ding, 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 ding. Whereas if it's a nice smooth sine wave, it's not being hit in the same way. That's what I put it down to anyway. You pays your money, you takes your choice, but if I were you, I would avoid modified sine wave inverters. Go for something that says pure sine wave on it. You're going to pay an awful lot more money for it, but it isn't going to make your equipment red hot, and it's not going to set your hand lamp on fire like it did my one I had in the garage years ago. So pure sine wave is the way to go. Don't use modified sine wave. Well, I don't know about you, but I think we'll call it a day at that. Talk about flogging a dead horse. Hopefully next time I'll find something more interesting to do. Until next time, thanks for watching. That'll do. Bye for now.